Hello, everyone. Welcome to my exam 3 review. We're already on exam 3. Just a reminder, we have 6 total tests for this class. So we're about halfway there. Yay, it's a midterm. So I just sort of want to break down how I'm going to be doing this review today. So what I'm going to be doing is I'm going to be going over each of the topics that Dr. Daddy has sent us about what we should focus on for this exam. Now, the way that I'm going to do it is going to be a little bit different than just going down the list. For example, like I'm going to go over Sn1 and Sn2 at the same time. And then what we're going to do is after we finished a big section, I'm going to write down some questions for you guys. And if you're watching on YouTube, you can pause and try to work them out yourselves, and then we'll work them out together afterwards. All right? So, I know that again, some of these things are listed under certain headings, like SN2 is asking you about the energy diagram, that type of stuff. I'm gonna go over energy diagrams first, then carbocations, and then we'll talk about SN1 and SN2 because both of those sort of topics, energy diagrams and carbocations, sort of lead into SN1 and SN2, E1, E2. All right? Oh, and by the way, a lot of people think that this content is a lot easier than stereochemistry and stuff like that. So if you had a hard time with stereochemistry, this could be sort of a good break-ish, hopefully. All right. So first we're going to go over energy diagrams. All right, so the idea behind energy diagrams is basically we have our reaction on the bottom, it's going forwards to the right, and then we have something called delta G on our y-axis. Delta G is Gibbs free energy. You should have sort of talked about it a little bit, at least in Gen Chem, but delta G is generally the formula of delta G equals delta H minus T delta S. And so the idea behind delta G is that if delta G is negative, that means we're releasing energy. We're going from something high to something low. So that is going to be exothermic. Oops, that was not written very well. Exothermic. If you have a positive delta G, it'll be just the opposite. We're going from something low to something high, so we're going to be endothermic. And I'm sure you've sort of heard about this before, but if you're exothermic, then you're generally going to be spontaneous. If you're endothermic, you're going to be non-spontaneous. But again, this is all stuff from Gen Chem. I'm just doing a quick refresher. Now, delta H is the change in enthalpy. So delta H is generally the bond energies, whereas delta S is sort of the measure of the disorder in the system. So for example, if I have a square, there's only one way I can orient that square. But if I cut that square in half into 2 rectangles, there are a bunch of different ways I can organize those rectangles. I can move them around each other, all of that stuff. So we would say that the disorder in the system would go up in this case. So delta S is entropy, also called disorder. Okay? Now, luckily for us, in organic chemistry, and T is obviously going to be temperature. In organic chemistry, a lot of the time, the entropy isn't going to matter as much as the enthalpy. So some of the time, you may see your energy diagram, instead of having a delta G, being a delta H. Because a lot of the time, this minus T delta S doesn't really apply to us. But just keep that in mind that this is the whole Gibbs free energy equation. It's just sometimes in this class, we're going to kind of ignore delta S. We don't think it's big enough to worry about. All right, so that's sort of the anatomy of a energy diagram. Let's talk about what an energy diagram tells us. So obviously, if the reaction is going left to right, our reactants are going to be somewhere over in this box, and our products are going to be somewhere over here. Again, if we're going to be exothermic, our reactants will be higher in energy than the products. Okay? Oh, somebody asked, how does temperature affect the spontaneity? So temperature is sort of associated with disorder. So the higher the temperature is, the more that will affect our reaction. But again, we're sort of ignoring T delta S for now. Again, that's going to be more important in stuff like biochemistry and gen chem, that sort of thing. But for this class, we're sort of going to ignore T delta S. But temperature will come into play later when we talk about elimination reactions. But again, we'll get to that in a second. Okay? So going back to this energy diagram, so this is an example of an exothermic reaction because our reactants are higher than our products. Now, of course, every reaction will have this sort of region in the middle, this orange region here. This orange region is going to contain something called our activation energy, EA. This is the energy we sort of have to get over in order to have our reaction happen. In addition, this EA, this point right here, that's going to contain something called a transition state. So I'm going to put transition here. So the transition state is sort of an in-between state between the reactants and the products where we do not have full bonds. Instead, we'll have like partial bonds sort of represented by a dotted line. So let's say we start with A, B, and then C is on its own, and then we end up with A, C, and B on its own. The transition state would look like this, where B is in the process, the AB bond is in the process of being broken, and the AC bond is in the process of being made. This is the in-between portion. This is the transition state, okay? So what I've shown you so far, this is a single step reaction. But if we have multiple, or we also call single step reactions concerted reactions. I'll write that down real quickly, concerted. So concerted means one step. But we can also have reactions that have multiple steps. So again, we're going to have delta H here, our reaction coordinate here. We'll have our reactants, we'll have our products. But now we'll have two transition states. And so now we can see that we have two activation energies. So again, the activation energy will have a transition state, but this valley between them, this valley is going to have an intermediate. It's important to note that intermediates have full bonds. So it'd be like A, B, C over here, that turns into A, C over B. The intermediate may be A plus. The activation energy 1 may have A and B in the process of being broken, and the second transition state here may have a C in the process of being made. So we can see here, this is a two-step reaction. We call reactions with more than one step stepwise reactions. Somebody said, what is the name of the A transition state being drawn on the left? Oh, yes. So always transition states are usually drawn with brackets with this double dagger here. I just didn't draw it in yet because I didn't think it was super important. But again, a lot of the times, again, we'll have partial negative and partial positives in our transition state, but I don't quite want to get into that now. I'm going to get into the partial negative, the partial positive when we actually get into actual atomic examples. Yeah, no, you're fine. And again, like somebody said, is that we will have this double dagger sort of representing a transition state. Somebody asked, can concerted reactions have intermediates? I don't think so. I'm not gonna say no or never, because there's never a never in organic chemistry. But concerted reactions don't really have intermediates because again, it's only one step. You're either the reactant or you're the product. You're not going to be somewhere in the middle. Whereas with stepwise reactions, you can have the reactant, the product, and then a sort of pit stop in the middle. So both of these are, can you tell from an equation if it has multiple transition states? If it has multiple activation energies, then it will have multiple transition states, okay? So like for example, this one over here, this reaction diagram on the right, it has two activation energies, so it has two transition states. One where AB is being broken, one where AC is being formed, okay? Does that make sense to everyone? Okay. So I've drawn here two reactions that are exothermic. We can also do the same thing with endothermic reactions. Oops, sorry, I just drew another exothermic reaction. So if we have something that looks like this, or something that looks like this, again, both of these are endothermic reactions. I just use exothermic reactions to show you these different states, okay? Is everybody with me on the idea of energy diagrams and how we read them and look at them? Yeah? Okay, awesome. So let me clear my screen. So now we're sort of going to shift gears and we're going to talk about carbocations. And I know this seems like a sort of a random topic to just sort of talk about right now. Somebody said, so in an endothermic reaction, we are not getting new products. Actually, whatever reactions that you have, you're always going to have reactants and you're going to have products. It's just, so I'm going to draw two new reaction diagrams here. In an exothermic reaction, your reactants are higher than your products in energy. Whereas in an endothermic reaction, your products are higher than your reactants in energy. So for like an endothermic reaction, we had to add energy in order to get to that higher energy state. Whereas in an exothermic reaction, we could give off energy to get to that lower energy state. Okay? And endo is basically the opposite of exo, what we're concerned with. Okay. So back to carbocations. And again, this sort of seems like a random topic, but both energy diagrams and carbocations sort of feed into the reaction types that we'll be talking about pretty soon. So carbocations, basically anything that has a carbon with a positive charge, because it's called a carbo for carbon, cation for positive charge. You can also have stuff like carboanions, carbon radicals, etc., etc. But for now, we're just going to be talking about carbocations. Okay? So first, we're going to talk about the stability of carbocations. So let's say we have our positively charged carbon right here. We have a carbon, a CH3 right here. And then it has two other bonds. Again, one thing to note is that the carbocation will be sp2 hybridized. Because, again, if we were to do the formal charge, carbon has 4 valence electrons, minus 3 bonds, minus 0 electrons in lone pairs equals +1, which is our +1 carbocation. In addition, sp2, we can see that this carbon has 3 electron groups around it. So that means that we are going to be sp2. Just a reminder, sp2, we can think of it as 1s plus 2p equals 3 electron groups. Okay? We can also have carbocations that are not sp2, something like this, but most of the time we're going to have sp2 carbocations. And it's a pretty safe bet to say that our carbocation will be sp2 hybridized unless it has some sort of double bond somewhere. Okay? All right, so let me erase this. All right. So back to this. So whenever we have a carbon that with a positive charge, sp2 hybridized, it's going to have an empty p orbital because remember there are 3 p orbitals. If we have sp2, then one of those p orbitals is not being used, and that's sort of represented here by this orange bubble. So essentially what happens is when we have a carbon group next to our carbocation, it's going to sort of share some of its electrons in one of its bonds with that empty p orbital. This is something called hyperconjugation. Usually we talk about conjugation. I hope I spelled this right because I'm talking and I'm writing and I always spell things wrong. Anyways, so we usually talk about conjugation alone with double bonds, resonance structures, that sort of stuff. We call this hyperconjugation because it's not exactly that. Instead, we are sort of sharing electron densities in these bonds here with the empty p orbital, which stabilizes that p orbital, which stabilizes our carbocation. So as a result, the more carbon groups our carbocation is attached to, the more stable it is. So this example here, this would be known as a primary carbocation because it's only attached to one other carbon. Okay? If this carbon had 2 carbon groups attached to it, then we would call it secondary. And again, this would be more stable because now this other carbon group is going to participate in hyperconjugation and thus stabilize that positive charge even more. So a secondary, somebody said, how is hyperconjugation different from inductive effects? So inductive effects are done by using an electronegative atom. So something like fluorine. Fluorine's very electronegative. When it's attached to something with a negative charge, I'm just going to put X with a negative charge here, it's going to pull that negative charge towards itself. In hyperconjugation, kind of what's happening here is the opposite. These guys are giving a negative charge to the positive charge. Can you explain hyperconjugation again? Let me explain hyperconjugation again, and then we'll talk about what makes something primary, secondary, and tertiary. But the idea of hyperconjugation is that when we have an sp2 carbon, the idea is we have one s orbital filled and two p orbitals sort of taken up by that hybrid orbital. That means we have one empty p orbital. That would be this that I've drawn in orange. P orbitals are generally drawn like this, where we have two sort of barbells on either side. Usually they're different colored, blah, blah, blah. All you need to know right now is that we have this empty p orbital here. And so what happens is that p orbital, it really wants some electrons. It really, really wants electrons. And so what happens is that these carbons sort of, they're like, oh, you're so sad without your electrons. And so what they do is they sort of donate some of their negative charge from these other bonds right here. These could be hydrogen bonds, they could be other carbon bonds, they can be other bonds. I'm just using hydrogen here because that's usually what you're going to see drawn, like if you look up hyperconjugation. So essentially what happens is these carbons take pity on our carbocation and they sort of donate some of their electrons. And the way that this sort of works, it's going to be kind of hard to describe, but it's slightly as if they're giving a partial double bond. This isn't completely correct, but this may help you understand the word hyperconjugation because we're not exactly giving it a double bond, so we're not exactly doing conjugation, but we're doing something similar. So we'll call it hyperconjugation. Does that sort of help you understand how hyperconjugation works? Oh, somebody said, can you write out a definition for it, please? So adjacent carbons give some electron density to a positively charged carbon. Okay? So this is the general idea. You don't really need to know the ins and outs of hyperconjugation. Just know that hyperconjugation is what stabilizes that carbon with a positive charge. When you get into Orgo 2 and beyond, you'll learn about electron donating groups and electron withdrawing groups, and a lot of these work in the same way. It's just in this case, this guy will be donating electrons. Oops, that is a text I wanted to draw. These guys will donate negative charges to that positive carbon. And again, it's different from induction because induction has just a regular non-charged atom that sort of pulls negative charges towards itself because it is electronegative. So like for example, this X here, it doesn't even have to be charged. This induction will just pull negative charges in general towards itself, okay? Does that sort of clear up hyperconjugation and versus induction and all that stuff? Okay, awesome. So I'm going to remove this over here just so I can have a little bit of room. I'm going to keep this definition up, and then we're going to talk about how to tell if a carbon is primary, secondary, or tertiary. So let's say we have our carbon, let me do it in black. So let's say we have our carbon with our positive charge right here. So the idea is if it's attached to one other carbon and two other hydrogens, it's a primary carbocation because it's only attached to one other carbon. A carbocation that's attached to two other carbons will be known as a secondary carbocation. And finally, a carbon attached to three other carbons will be known as a tertiary carbocation. And again, we cannot have quaternary carbocations because then that would give the carbon four bonds, and then it would be neutrally charged, and it couldn't exactly be a carbocation. So we can see here that as we add, oops, that's an eraser, that as we add carbons, that hyperconjugation effect is going to increase, because in primary carbocations, this guy is going to give negative charges. Then secondary, both of these guys are going to give negative charges. And in tertiary, all three of them are going to give negative charges. So we can see here that the tertiary carbocation sort of gives more negative charges to that positive charge, thus sort of stabilizing it. And again, stabilizing it in that we're making it more neutral, because generally the more neutral you are, the more stable you are. So this is why tertiary carbocations are more stable than secondary, which are more stable than primary. There's one more type. Somebody said, again, can you define hyperconjugation, please? So I'm going to repeat this one last time, and then I have to kind of move on because I'm spending a lot of time on this idea of hyperconjugation. But essentially what's happening is these adjacent carbons, they say, wow, this poor carbon next to me has, I'm going to sneeze. Okay, it's gone now because I said I was going to sneeze. Anyways, so this carbon here on the right sees that this carbon in the middle has a positive charge and thus a vacant p orbital, a p orbital with no electrons in it. And so it says, oh, I feel so bad for this empty p orbital here. I'm going to sort of loan some of my electron density to it in order to make it more stable. So essentially what happens is carbons adjacent to our carbocation are going to give some of their electron density, not through resonance, not through a full bond, but through hyperconjugation in order to help stabilize that positive charge. Inductive effects are only really involved in cases where a much more electronegative element is present. Exactly. Okay? Does that make sense to everybody? Okay. I'm going to dive into one other type of carbocation, which you may have seen on your homework. We didn't really talk about it much in class, but it's something called an allylic carbocation. So allylic basically just means we have a double bond next to the atom with either a charge or a radical or whatever. In this case, a positive charge. And essentially what can happen here is that we will have a resonance structure where we will sort of share the double bond and thus share the positive charge. And again, remember, the true structure of a resonance structure is sort of a hybrid between the two. So we can see here that in this case, we can see that the positive charge isn't fully on any one of these carbon atoms. And if you remember from the acid-base sort of segment that we talked about, when we are delocalized, when that positive charge is delocalized, we like it better because it stabilizes it. So we would say an allylic carbocation is more stable than a tertiary carbocation. This should not come up too much in this section in many of these tests. I just know your book mentioned it, so I also want to mention it. These allylic carbocations and the idea of allylicness will come in more during radical reactions and more in Orgo 2. I just want you guys to know that this is something that exists and is more stable than a tertiary carbocation. Okay? So that's sort of the rundown with carbocations. Do you think he may test us on that? I don't see the tests, so I don't know exactly what he's going to test you on. just sort of know in the back of your mind that if you have to choose between an allylic carbocation and a tertiary carbocation, the allylic carbocation will be more stable. And again, we'll get into what this means for our reactions a little bit later. I just want everybody to understand what a carbocation is and what makes it more stable. Okay? All right. So I'm going to clear this screen now, and then now we're going to actually get into Sn1 and Sn2. Okay. So Sn1 and Sn2. I'm just going to put Sn right here. Sn stands for substitute. I am awful at spelling, so please bear with me if I spell something wrong. But Sn stands for substitution. So Sn1 and Sn2 are generally going to have the same sort of beginning product and the end product sort of superficially. So we're going to start with an R group. And just a reminder, an R group is just an alkyl group, which is just sort of a string of carbons. So this can be like a string of carbons that looks like this, a string of carbons that look like this. R is just a placeholder for any string of carbons attached to an X group, which will be a halogen. So again, halogens are the second to last column on our periodic table. So stuff like fluorine, chlorine, bromine, and iodine. Okay? So altogether, we're going to call this an alkyl halide because we have an alkyl group attached to a halide group, a halogen. Okay? So we start with an alkyl halide. This is going to be our substrate. And a lot of the times, in this class, we'll consider the substrate the actual group with the carbons. Whatever we're reacting with it will usually have a different name. Like in this example, when we do substitution, we're usually going to do it with a nucleophile. This nucleophile may have a negative charge or not, but we know it's going to have a lone pair. And just a reminder, nucleophiles, so let me write that all out. Nucleophiles, they love nucleuses, aka positive charges. Okay? Does that make sense so far? Okay, so the substrate is always the alkyl halide. In this case, yes, I would say 99.9% of the time, in this case here, our substrate will be the alkyl halide. Okay. So what generally happens in our substitution reaction is our nucleophile is going to replace our X group, our halogen, and then our halogen will end up sort of on its own somewhere. Okay? And the reason why this whole reaction can even happen is because, remember, our halogen is very electronegative. So by the inductive effect, which we talked about a little bit earlier, it's going to have a partial negative charge, and the carbon it's attached to will have a partial positive charge. Okay? And we'll get all into that later. This is just sort of the general gist of a substitution reaction. We substitute the halogen with some sort of nucleophile. Okay? Does that all make sense so far? Okay, awesome. So I'm going to go ahead and erase this so I can have my screen back so I can write some more. So when we talk about SN reactions, we can either have SN1 or SN2. So the big difference between Sn1 and Sn2 is that Sn2 occurs in one single step. So the way that we would write the mechanism, aka how the electron moves, is first off, this bond here, this bond has to break because again, carbon can only hold 4 bonds. So that means that to make a new bond with the nucleophile, it has to get rid of one of its old bonds. In this case, that would be the bond with the halogen. So our halogen is leaving the reaction. So we're going to call that our leaving group. Okay? The second part of this mechanism will be the nucleophile grabbing on to that carbon. We're going to call this the nucleophilic attack because it's sort of attacking that carbon with its lone pair, and then we end up with our single step here, our single step reaction, R attached to the nucleophile plus just our leaving group on its own. Okay? Now let's remember our energy diagram. So I'm going to go ahead and draw our energy diagram. So this is a one-step reaction. This is going to be a concerted reaction. So this can be either endothermic or exothermic. I'll draw both of them here. So here's our exothermic, Sn2, and here is our endothermic, Sn2. Okay? Does that all make sense to everybody so far? So we can see here how this idea sort of is represented in these sort of reaction diagrams, okay? And again, we're going to have a transition state at this top point here at the activation energy. And like before, we'll say, okay, so the activation energy is going to include the leaving group bond breaking and the nucleophilic bond forming, okay? And so we can also say that, okay, so what happens in this reaction is the nucleophile is going to be partially negative, the carbon, the R group, will be partially positive, and the X group will be partially negative, again, because due to the electrophilicity of the X group, the halogen, it'll be partially negative, and the R will be partially positive. Somebody said, so the loss of leaving group and nucleophilic attack happen simultaneously. Yes, for this class, we're just going to say they happen simultaneously, okay? And we can see that this is our transition state, where the bond is partially being formed and the bond is partially being broken, okay? So, one more thing that we, oh, go ahead.
Sorry, I just had a question. Does it matter what side we put the bond breaking and the bond forming on? Like, does the bond breaking have to be on the right side of the R?
Opposite sides.
Okay.
Generally, when you draw these transition states, you kind of want them to be as close to sort of the reactant as possible. So, like in this example, I drew X on the right because I drew the substrate as having X on the right, but it shouldn't really matter too much, okay?
Okay, thank you. Because in the book, it didn't specify which side. It just put them on like different sides.
Yeah, it doesn't really matter, but just for the sake of consistency, I like to have it sort of near the substrate, okay? And that actually brings me to the next point, the idea of the transition state. So anyways, so this transition state, it's going to either sort of be sort of more or it's going to be more reminiscent of either the reactants or the products. And that's just a matter of which one is closer in energy. So if the reactants are closer in energy to the transition state, aka taller or higher up in energy, then our transition state are more likely to sort of resemble our reactants. So, like for example, in the exothermic, the R and the X would sort of be closer together than the R and the nucleophile, just because it's going to sort of look more like our reactant, and it's just going to be the opposite in our endothermic reaction. The transition state is closer to our products than it is our reactants, so the nucleophile is going to be closer to the R group than the X. But this doesn't really matter too much for us. All we really need to know is that, okay, if our transition state closer to the reactants, it's going to look like the reactants. If our transition state is closer to our products, it's going to look like the products. And we should be able to draw that transition state. Okay? Does that all make sense to everybody? Okay, awesome. So let's recall, okay, so I'm asking you to remember a lot from Gen Chem, but let's remember the rate equation. So the rate equation basically means how fast is a reaction going to go. So somebody said, so Sn2 can either be endo or exo. Yep. Any of these reactions can be endo or exo. It just depends on what specific reaction you're doing. All right, so anyways, remembering the rate equation is R equals K times the concentration of our reactants. Okay? So I'm just going to put boxes here, A, B, to represent reactants. Okay? Somebody said, isn't there another mechanism for Sn2 other than concerted? The other mechanism for substitution that is stepwise is Sn1, and we'll get into that in a second. I just want to cover the rate equation for Sn2 very quickly. Is it relevant that we know whether the Sn2 reaction is exo or endo for the test? So basically a question that they could ask on the test, it would be like, select the reaction graph the reaction graph that is endothermic Sn2. And so you'd say, okay, Sn2 is a one-step reaction. I know it's going to be endothermic, so this has to be my answer. That's sort of how you should know. You should be able to tell which graph is endo and exo, which one's one step, which one's two step. All right, so back to the rate equation. So if you remember the rate equation, it depends on the slowest step of our reaction. In this case, we only have one step. So as a result, that has to be our slowest step. And so then that means that our rate equation will include both the substrate and the nucleophile. Okay? And again, remembering way back into Gen Chem feels like 7 years ago. But what you would do to tell the order of the reaction, so like what order it is you would add the exponents of the concentrations together. So in this case, this is 1 plus 1 equals 2. The points where this would not be 1 would be like if you had 2a plus b yields c or something, then you would have a to the second, and we don't really have to worry about that too much in this class. So just know that Sn2 is going to be second order. And that, my friends, is where the Sn2 comes from, because it's second order. Okay? Does that make sense? Okay, awesome. Sorry. So like if I had 2a plus b yields c, then I would have a to the second and just b to the first. And so with our Sn2, they're both sort of 1 and 1. So we'd say Rx to the 1th, nucleophile to the 1th, 1 plus 1 is 2, second order. Okay, this equation here, this would be third order because 2 plus 1 is 3. But again, we don't have to worry about that too much. Sn2 is, again, I hate using the word always, but it will always be second order. Okay? Does that all make sense? Sorry. Somebody asked, what would be the slow and fast step in A plus B? Again, it's only one step, so A plus B would be the first. In the rate equation, this would be our slow step. All right?
I have a quick question.
Go ahead.
So, where you talked about the transition state, whether it's near the products or reactant,
Yes.
would that be useful when we're trying to find out if it's exothermic or endothermic, or how would we be able to use
I
that?
mean, it might be. It's honestly, I find it easier, and I think most people find it easier to see if something's exothermic or endothermic by just looking at the reactants or the products. A question would be like, would this transition state represent the reactants or the products more? And generally, it isn't always like this, but generally, if you're exothermic, you're probably going to represent or be closer to your reactants, so you're going to resemble your reactants more, and the opposite for endo. Does that make sense?
Yeah, it makes sense. So, like my question, kind of like, when would we use that? Like, the location, like how close it is to the product. Like, what would a
So
question?
a question may be like, so I give you this graph here, and I say, would the transition states more resemble the reactants, the products, and then just two other answers that are just sort of out there. You would say
Oh, okay.
that the reactants, since they're closer to the transition state, though the transition state is going to resemble the reactants more. Okay?
So, like, it would like favor the reactants more.
No.
Oh, okay.
Resemble. It wouldn't favor. Like again, favoring the forward reaction versus the reverse reaction, that's a free energy question that we probably shouldn't get into for organic chemistry because it's not as helpful for us. But just knowing whether or not like this transition state does it look more like the reactants or the products sort of thing.
Oh, okay. Thank you so much.
Okay. And yeah, this is called the Hammond Postulate. I just think that naming these things with weird names sort of obscures what's actually happening, but the idea that transition states are closer, they resemble what they're closer to, is the Hammond postulate. All right, so that is Sn2. So Sn1 is a little bit different. So what occurs in Sn1 is now we're going to have a two-step reaction. So let me just, oops, erase that. So first we start with our alkyl halide. Then we end up with a carbocation intermediate, and then we use our nucleophile, and then we end up with our new product. Okay? So there are two steps here. One where the leaving group leaves, one where the nucleophile attacks. Okay? And this is the root of Sn1. There may be more steps like a proton shift or a proton transfer, a hydride shift, whatever. But this idea here, this is the meat of an Sn1 reaction. And one thing to note here is that this first step is the slow step, and the second step is the fast step. I'll write that right here. Okay? So again, since this is a stepwise reaction with two steps, again, we can either be endothermic or exothermic. Here's one that's exothermic. Here's one that's endothermic. Okay? So we can see here that here is our X, which is our reactants. Here is our nuke, which is our products. Our nuke. And here is our intermediate, our carbocation. Okay? And again, here we're going to have two transition states. One where the RX bond is being broken, partial positive, partial negative, double dagger, and then one where our nucleophile bond is being formed. Again, partial negative, partial positive, double dagger. Okay? So here are two reaction diagrams. And again, when we talked about this is exothermic because the reactants are higher in energy than the products. So overall, the energy in the system is released. Even though this first step here is endothermic, overall the reaction is exothermic. Okay, and I'll just write that over here that this is endothermic. Okay. So again, Sn1 is a stepwise reaction with two steps. This first part here in both graphs, that's representing the reactants. This second part here represents our intermediate, our carbocation intermediate, and this here represents our product. These two hills here, they represent, or the first hill here represents our transition state where the leaving group is leaving. The second hill here represents the transition state where the nucleophile is being added. Somebody said, do we need to know exactly where the intermediate energy level is? Not really. Usually what you'll be doing is you'll be saying, again, choose the Sn1 endothermic graph. And you would say, okay, it has to be two steps. It has to be endothermic, so it has to be this one. Okay?
I have a
what?
question here. So, do we have to know whether it's slow or fast? And also, does Sn2 have like slow or fast?
So we have to know that this first step is slow because of the rate equation, which I'll get in a few seconds. Sn2, we don't need to know if a step is slow or fast because there is only one step. Okay? There is only one step, so it's both the slowest and the fastest step, if that makes sense.
Okay, thank you so much.
Okay. And the slow step will always be, I hate saying always, but again, for this class, it will always be this first step because it's harder to go from a more stable state to a less stable state, such as with the intermediate, than it is to go from the intermediate to our product. Okay? Does that make sense to everybody? Okay, awesome. So now let's talk a little bit about the rate equation. So again, R equals K times the concentration reactants of the slow step. We can see that the first step here is slow. We can also see the only reactant in this slow step will be Rx. So that means this is going to be a first order reaction because it's just going to be one. So this is going to be first order, thus Sn1. Okay? Does that all make sense so far? Okay. So these are sort of the big differences in how the reaction happens between Sn1 and Sn2. Does anybody have any questions about this? And again, we will get into how to tell if something's Sn1 or Sn2, but first I kind of want to get into the concept of how they're different, okay? Does that make sense to everybody? Okay, awesome. So I'm going to clear my screen now. And we're going to talk about Sn1 versus Sn2 actual products. So Sn1, Sn2, the main difference between the two of them in how or when we sort of in the lab, whether we choose to do Sn1 or Sn2, it sort of depends on what our products are going to be. So let's say that, instead of using Rx, I'm using an actual guy here. Let's say that we have these two reactants here. And let's say that we do an Sn1 reaction, we replace it with our nucleophile, we replace it with our nucleophile. Again, I'm not going to show the actual mechanism here because it's going to be more important later. I'm just showing you the difference in the actual products, okay? So Sn2. Whenever we do our Sn2 reaction, we know that our transition state is going to look something like this, where we have our X group over here and our nucleophile over here. Both of them will be partially negative, and the R will be partially positive. And so as we know, the negative charges are going to repel each other. So they're going to want to stay as far away as possible from each other. So let's draw this sort of in 3 dimensions. So like if our chlorine is on a dashed wedge, our nucleophile in the transition state is going to stay as far away as possible from the chlorine as a solid wedge. So when we do Sn2, we're going to end up with an inversion of stereochemistry just at the stereogenic center that had the leaving group. So for example, if I had a second stereogenic center like right here with OH or whatever, that stereogenic center stays the same because we aren't attacking that carbon. We are focused on this carbon right here and how the nucleophile and the leaving group interact, okay? Does that make sense? Oh, this is called inversion of stereochemistry. You may have seen this in the book. So inversion, you just do the opposite, okay? Let me erase these OHs.
Does inversion always occur for Sn2 reactions?
For Sn2, yes. Inversion will occur for Sn2. The racemic products that some of you are asking about will occur with Sn1, and we'll talk about in a second. So let me just finish up and explain Sn2 one more time. So Sn2, again, we have our transition state. We talked about this a little bit before. We have our transition state where both our nucleophile and our leaving group are attached to the same exact carbon. So let me fix this one down here very quickly. So if I were to draw like this transition state, for example, you can see here that the partial negative charges are going to push against each other and basically shove each other as far away from each other as possible. Sorry if that was a little bit of a mouthful, but so we can see here that the chlorine on a dashed wedge is going to sort of push against, it's not going to want to move from its dashed wedge position. So it's going to force the nucleophile to take the opposite position, aka the solid wedge position. Okay? It's sort of like if I had like a stick here and I have two magnets that are magically floating that are just magically floating on it. I know that these negative charges, they're going to repel. So as a result, they're going to want to stay as far away from each other as possible. Thus, they're going to be on opposite types of wedges. Okay? And yes, Cl does leave as the leaving group.
Does a Cl, do you do like
I'm not drawing the mechanism right now, especially because of Sn1, but if I were to draw the mechanism, it would look something like this.
Okay, but would we have the Cl as also a product, like just plus Cl minus?
Oh yes, it would be plus plus Cl as well. I just wanted to draw the product here.
Okay, so the full answer would have that, not just the.
Yes.
Okay, thank you so much.
Okay. There is no dash or, oh yeah, if there is no dashed or wedge, we won't have to worry about that. Like if our reactant looked like this, we would just draw our product as this, because there's no way for us to tell if we're going to end up on a dash wedge or a solid wedge without knowing what the leaving group was on. Okay? Does that all make sense so far? Okay, awesome. Oops, all right, there we go. All right, so that's why we will end up with an inversion of stereochemistry with Sn2. Sn1 is a little bit different because remember, in Sn1, we are going to create a carbocation, okay? When we create that carbocation, remember when we're a carbocation, we're sp2, which means we are trigonal planar. This planar is really important because that means that every atom on this carbon here, on the positively charged carbon here, is going to be in the same plane. So like, for example, if I drew this out, instead of having the hydrogen go out to either side, we would end up just having the hydrogen go straight up. Okay? In this way, it doesn't matter where our nucleophile attacks from because there is no negative charge forcing it to go one way or another. So as a result, we're going to get two possible products for Sn1. One where it looks like the product for the Sn2, where there's an inversion of stereochemistry, and one where there is a retention of stereochemistry. Let me write that down, retention. So stereochemistry stays the same. And so these are enantiomers, and as a result, we're going to end up with a racemic mixture. And a racemic mixture is basically a mixture of two enantiomers, where the enantiomers are the exact same amount. So there's an equal amount of both of these enantiomers in our mixture. Okay? It's important to note, though, that sometimes we will not end up with a racemic mixture. For example, somebody said, I thought there was more inversion. That is not the case. We end up with a racemic mixture where everything is equal. One thing to note, though, is to look out for what if we make diastereomers. So if you remember, I know we're coming back to chapter 5, oh no. Diastereomers are partial mirror images. So you can see here that this nucleophile is mirror imaged with this nucleophile, but the OHs stay the same. So we can obviously see here that these two, instead of being enantiomers, they're diastereomers. And I'm not going to try and spell the whole thing. All right, so does that make sense? Okay.
Can you kind of repeat that?
Yes, okay. So when we only have the single stereogenic center, so the only one with just chlorine, then we will end up with enantiomers. But if we have another stereogenic center on our reactant, then we will end up with diastereomers. Okay? So just to reiterate, Sn1 will have the nucleophile either attack from the front or the back because there is no negative charge to push it one way or another. Because remember, in Sn2, we end up with negative charges pushing against each other, forcing the nucleophile into the opposite position. Whereas over here, Sn1, we do not have that negative charge, so we can attack from either side of that positively charged carbon. Okay? Does that make sense?
Yeah.
And when we have diastereomers, we'll have equal amounts of diastereomers, but we don't call it a racemic mixture. A racemic mixture is a specific term for a mixture with an equal amount of each enantiomer. Okay?
Would the Cl also be, so you'd have the one with the
Yeah,
dash?
it would also be here.
Okay, I just wanted, because for the homework I kept getting it wrong.
Yeah, I just wanted to. I'm just right now. I'm just focusing on like the carbon, the stereogenic center changing rather than writing out the full product. So that's why I'm dropping the Cl negative, but it is
And also,
there.
so for example, would you have, so you would have the one with the dash and the filled in one, you would have plus between them, or you just like
Yes, you would have a
them?
plus between them.
Okay, thank you so much.
So what do you need to know regarding diastereomers? You should just know how to sort of you should know how to recognize one. So like, for example, you can see here that, we can see that we have opposite stereogenic centers here, but not opposite ones here. That makes it a diastereomer. Remember, diastereomers have a partial change. And yeah, it may very slightly favor the inverted conversion as far as Sn1 goes, but for our purposes, we are just going to say it makes a racemic mixture. So a diastereomer mixture, we cannot call that a racemic mixture because, for example, the diastereomers between these two, so like if I had two diastereomers here, I'm sorry, not diastereomers, but enantiomers, they would look like this, where they're perfect mirror images with perfectly opposite stereogenic centers. When we have an equal amount of each of these enantiomers in a mixture, we'll call that a racemic mixture. However, up here, if we have equal amounts of each diastereomer, we can't exactly call that a racemic mixture because a racemic mixture deals with enantiomers and not diastereomers. Okay? Does that make sense?
Can I just clarify? Sorry.
Yeah, go ahead.
So in Sn1, it will always give diastereomer, not enantiomer. Sorry.
Oh, not always. I'm just saying you need to look out for diastereomers because if you have another stereogenic center, then you'll end up with diastereomers. But if that is the only stereogenic center, then you'll end up with enantiomers. Okay?
Okay, can you say that one more time? I just got to write that down.
So enantiomers, as far as Sn2 or Sn1, is concerned, we will form enantiomers when we only have one stereogenic center at the position of the substitution.
Okay.
We will end up with diastereomers if we have more than one stereogenic center.
Okay.
So yes, usually, most of the time, we'll end up with two products for Sn1 and one product for Sn2. And you may hear this called different attacks. So you may hear the Sn2 when we invert stereochemistry, we call that a backside attack because we're going from the back of our leaving group. Whereas here in Sn1, we have a backside and a front side attack because we're going from the same side as the leaving group for front side. Okay? So what kind of question could be asked regarding this? So the hardest question that a question that could be asked of this, I'm going to clear my drawing. If they give you some sort of Sn1 reaction, and then they give you different sort of products like labeled 1, 2, 3, and 4, and then you have like different answers, like A is 1 plus 2, B is like 1 only, that sort of thing. Where when we have Sn1 will end up with two products, and Sn2 ends up with one product. Okay? Well, we'll do more examples once we sort of get into what makes Sn2 and what makes Sn1 as far as like reactants, nucleophiles, that sort of thing. Okay? Does that make sense? Okay, perfect.
I had a question regarding diastereomers.
Go ahead.
So the OH wedge, because it was there, does that mean it's no longer racemic? When you
Yes.
drew?
Sorry, let me draw. Hold on. Let me draw the two products that I drew before. Yes, we would say that this is no longer a racemic mixture because we have diastereomers instead of enantiomers.
But it's still considered Sn1, right?
Yes, this is still an Sn1 reaction. It's just we have to take into account that an equal mixture of diastereomers is not going to be racemic, whereas two enantiomers will be.
Okay, so for it to be racemic, it always has to be enantiomers, or generally,
Yes.
usually.
Yes.
Okay.
Somebody said, could you do an example of a question if we have time? Yeah, we're gonna do quite a few example questions once we get to the end of Sn2 and Sn1 because I want to ask questions that combine all of these different factors together. Okay? All right. All right, so now we've talked about what makes Sn1 and Sn2 different in terms of the actual reactions, like what kind of products we get, the different reaction diagrams. Now we're going to talk about how to tell if something's actually going to be Sn1 or Sn2. So, Sn1 versus Sn2. Sn1, Sn2. So the first thing we're going to talk about is sort of the alkyl halide. So what kind of Rx we have attached to, such as primary, secondary, tertiary. I almost said secondary twice, that sort of thing. So remember, we just, well, not just, but we talked about carbocations earlier here. And so now that's going to come in to the Sn1 reaction, because remember, when we do the Sn1 reaction, we end up with a carbocation intermediate. And so this is going to feed into the idea of the stability of carbocations. So the idea here is the more stable the carbocation, the more likely Sn1 is going to react. So again, we know that tertiary carbocations are more stable than secondary, which are more stable than primary, which are more stable than something called methyl. I don't think I mentioned methyl, but the idea of a methyl carbocation is a carbon with 0 carbon-carbon bonds, and it's just sort of like a methyl group. Methyl meaning 1 carbon. But the idea here is now we're going to apply this to our alkyl halide. We're going to have a primary alkyl halide where we have our halogen attached to a carbon attached to one other carbon. We call this a primary alkyl halide. We can have a secondary alkyl halide, which is when we have our halogen attached to a carbon that is attached to 2 other carbons. Here we are defining it as primary, secondary, not in relation to the halogen exactly, but more in relation to the carbon attached to the halogen. And then of course, tertiary will look something like this. Okay? So then tertiary is going to be preferred over secondary, which is going to be preferred over primary. And then we almost never see methyl react in an Sn1 fashion. Okay? So we can see here that for Sn1, because we make that carbocation and we want to make the most stable carbocation possible, we're going to prefer tertiary over secondary over primary. Again, you may see something like this, where we would call this an allylic carbocation, or not a carbocation, but allylic alkyl halide. This is going to be the most reactive. But again, you won't see this as much in this section because it's a little bit more complicated than you guys are sort of trained to understand at this point. Okay? So generally, allylic is more reactive than tertiary, but you will not see it very much. Okay? All right.
For the comparisons that you did for like tertiary, secondary, primary, is that regarding their stability or regarding their energy?
I'm unsure what. Can you ask that question again in baby words so
Sorry,
I can
maybe
understand?
I worded. Okay, I'm sorry.
No, you're
so,
fine.
like,
I have the mentality of a second grader, so I just need some help.
Oh. Okay, so is tertiary more stable than secondary and secondary is more stable than primary?
Yeah, exactly.
Or like does tertiary have more energy? Okay, it's stability.
So the idea here isn't how stable these are. Oops, my pen messed up. Isn't how stable these are. Rather, it's how stable their corresponding carbocations are. Okay?
Thank you.
Actually, this is going to sort of mess you guys up. The more stable your carbocation, the more likely you're going to react for Sn1. This is sort of the same idea of when we talked about acids and how strong they are. So remember, the stronger, the M here, that M represents methyl. So remember, the stronger the acid is, the more likely it's going to dissociate into its conjugate base. The more stable your conjugate base, the more likely it will dissociate. The same idea is here. The more stable your intermediate, the more likely you'll create that intermediate. Okay? Does that make sense to everybody? Okay. So Sn1 will generally react with secondary and tertiary carbocations. Exactly. So Sn1, they really like these tertiary and secondary. They don't like the primary and methyls as much. But it, like, technically, if you do something crazy to it, it can do primary and methyl, but we won't see that in this class. So is a primary carbocation more like to be Sn2? We're going to get into Sn2 in just a second. I just want to make sure everybody understands the concept of Sn1 and the carbocation stability. All right, awesome. So now let's look over to Sn2. So the idea of Sn2, so the cutoff is secondary. Generally for Sn1, yeah, the cutoff will be secondary. Okay. So talking about Sn2, everything happens. Oops, that is the wrong color. That's P colored. Generally, the idea with Sn2 is that everything happens in a single step. So in Sn2, we kind of have a need for speed. The faster this reaction can occur, the better. So the idea here is let's say we have something like a tertiary alkyl halide. What will happen here is the nucleophile is going to have to sort of maneuver its way around those big groups, and it doesn't really like that. So here, Sn2 doesn't like tertiary because of something called let me get my steric hindrance. This steric hindrance is basically these groups here sort of pushing the nucleophile away and not letting the nucleophile get into this carbon here in order to attack. So the less steric hindrance we have, the better. So the less carbon groups we have, let me erase, the less carbon groups we have, the better. So in this case, Sn2 will prefer methyl over primary, over secondary, over tertiary. So yeah, it doesn't really have time to go around all of these different carbon groups here. So as a general rule, Sn2 will occur with methyl primaries and secondaries. So secondary is where we get kind of an overlap. And so when we get to secondary, we're going to have to sort of take into account the other factors. I just want to make sure you guys first understand the concept of how the alkyl halide sort of causes Sn1 over Sn2 or vice versa. Okay? All right. So a lot of the times, the first thing you're going to want to look at is our alkyl halide. However, if our alkyl halides sort of overlap, so if it's a secondary alkyl halide, we're going to have to look at the next factor, which is the nucleophile. So we haven't talked about the nucleophile too much right now, but there are generally two types of nucleophiles. There's going to be a strong nucleophile and a weak nucleophile. I'm just going to put STR for strong and WK for weak. Generally, a strong nucleophile is going to have a negative charge, and a weak nucleophile will be neutrally charged. It'll usually be neutralized by some sort of hydrogen, okay? But it's still going to have a free lone pair in order to react. The idea of a nucleophile is it has a lone pair to react, whether it be strong or weak. Yes, there is one. Oh, so generally strong nucleophiles will be negatively charged and weak nucleophiles will be neutrally charged. It'll usually be neutralized by a proton, aka a hydrogen. But that nucleophile will still have a lone pair to react in order to create a new bond. And yes, the exception to this rule is fluorine minus. This is a weak nucleophile just because it's so small and so electronegative. But you won't really see fluorine work as a nucleophile in this class. More often, you'll see other nucleophiles, and I'll write examples for that. Okay? So an example of a strong nucleophile would be OH negative, and its corresponding weak nucleophile would be H2O. So you can see here how both oxygens have lone pairs to donate. It's just this is a negative charge, so it's going to be a strong nucleophile versus a weak nucleophile. Okay? Does everybody understand the difference between a strong nucleophile and a weak nucleophile? Okay, awesome. So when we're talking about Sn1 versus Sn2, what happens in SN2 is that we're going to have our nucleophile interact directly with a partial negative, whereas we're going to have SN1, it's going to interact with a full positive charge. So in this case, SN2 will prefer a strong nucleophile. And this is because that full negative charge is more likely going to be attracted to this partial positive. Okay? Whereas over here, unless we have a full positive charge, our nucleophile will not react. And this is a good thing because we want to wait for that first step in order to form that carbocation. So basically, the weak nucleophile will be polite and it will wait for that carbocation formation in order to do a nucleophilic attack. Okay? Does that make sense? Yes. So SN2 prefers strong nucleophiles and SN1 prefers weak nucleophiles because SN1, it wants to have a chance to create this carbocation. And if we use a weak nucleophile, that gives it plenty of time to form that carbocation. Whereas over here, SN2 has a need for speed. So it wants to go as fast as possible. And with a strong nucleophile, you can go faster. Okay? Does that make sense?
Does the strength of the nucleophile correspond with the base? I'm not sure.
So nucleophiles will be bases. Not all bases will be nucleophiles. And we'll talk about that in a little bit. But for right now, let's talk about the simple, strong, and weak nucleophiles. I just want to make sure everybody's on the same page here.
Okay, thank you.
I'll talk about bases that are not nucleophiles when we get into elimination reactions. For now, let's just keep things simple and then go into that. Is that okay?
Yes, thank you so much.
Okay, awesome. All right. So SN1 prefers weak nucleophiles, SN2 prefers strong nucleophiles. Okay. There are two more factors we need to consider. One of them is going to be what kind of solvent we're doing things in. So we can either do this in an aqueous or a protic solvent or an aprotic solvent. And let's talk about the difference between the two of them. So basically, all solvents that we are going to have are going to be some sort of polar solvent. But what sets these apart is if they're polar protic or polar aprotic. And this is pretty easy. A protic solvent has hydrogen bonding. So for example, water is a protic solvent because OH is a hydrogen bond. An aprotic solvent doesn't have any hydrogen bonding. For example, acetone, which is what we have here, is aprotic because while it does have carbon-hydrogen bonds, these are not hydrogen bonding bonds. So stuff like NH, OH, or FH count as hydrogen bonding. So if we have any one of these bonds in our solvent, then we consider it to be a protic solvent. Okay? Does that make sense to everybody? Okay, awesome. So
Yep.
the idea between protic versus aprotic solvents is protic solvents are way more likely to have strong partial negative and partial positive bonds. And if you remember in Gen Chem, God, so long ago, so very long ago, when we dissolve something like a salt in water, which is a protic solvent, the positive charges will sort of surround any negative charge in the water, sort of isolating it from any other charges. Same with the positive charge. So we can see here.
Aprotic.
Go ahead. Sorry.
I'm so sorry that I'm cutting you off.
No, you're fine.
For protic and aprotic, are they SN1 or SN2 reactions?
We'll talk about that in a second. I'm just defining protic versus aprotic.
Oh, okay.
Like
My bad.
ignore this is not part of like my list here. I'm going to erase and make it a little bit more obvious. But right now I'm just describing protic versus aprotic. Okay? All right. So whereas aprotic solvents tend to have less sort of intense partial charges, it's still going to separate somewhat. So it's going to, like, it may use a negative charge to separate a positive charge out, but it's less likely to separate the other negative charge as much. Okay? So that's where the big difference comes in. Protic solvents will completely isolate our portions of our reaction, whereas aprotic sort of isolates only partially. So again, our Sn2 with a need for speed does not want to be separated. It wants to be as close to each other as possible. So Sn2 prefers aprotic solvents, whereas Sn1, it wants time to make its carbocation, so it prefers protic solvents. Okay? Does that all make sense so far? All right, awesome. So let me erase this very quickly. And so there's one last thing that we have to talk about. This next factor has to do both with Sn1 and Sn2. Oh, sorry. So Sn1, protic solvents. Protic solvents sort of they isolate each part of a reaction. They slow the reaction down. They let it take its time. So Sn1 likes to take its time in order to form its carbocation. So that's why we prefer protic for Sn1. Whereas Sn2 wants to happen as fast as possible, so it does not like to be separated. That's why it prefers aprotic, because it only partially separates things. Okay? Does that make sense? All right. So let me erase this very quickly. All right. Oh, that was not the erase button. All right.
I have
Go
a
ahead.
quick question.
Go ahead.
So would NaOH, would it be protic or aprotic?
That NaOH? Wait.
Yeah.
That would be your nucleophile.
Oh, okay.
Because so one thing to know about nucleophiles, sorry I cut you off there. Whenever you have a metal attached to something else, it'll dissociate into Na plus and OH minus. So in this case, the NaOH would be considered a strong nucleophile because it dissociates into Na plus and OH minus. OH minus is our strong nucleophile.
Okay, so the solvent it's not the nucleophile, right?
Right, the solvent and the
think I got it.
nucleophile are different things unless you're doing something called solvanolysis.
Yeah, I think that's what where I
Yeah,
read that
so
before.
solvanolysis is basically the idea where our nucleophile is the same as our solvent. It's like we're doing we're using H2O as both the solvent and the nucleophile. Okay?
So do you know like how we can know if it's that or just a nucleophile?
A lot of the times they'll tell you like
Okay.
something the solve. Let me see if I can spell it. Solvanolysis. Something like this. So something that's sort of this spelled adjacent is going to include the nucleophile as both the solvent. There's like a special name for it. Okay.
Okay. Thank you so much.
All right. No problem. Oh yeah, I'm gonna go through everything today, even if it takes 3 hours. Anyways, so there's one last thing that we should talk about as far as Sn1 and Sn2 go. This is less of a difference and more of a trend. So both of these will do the same exact thing, and this has to do with the leaving group. So again, we talked about how the leaving group is going to be this halogen here. So let's think of this in relation to acid base. Bear with me. So let's say that we have HBr versus HCl. I know I'm asking you a lot, but which do you think is going to be more acidic? HBr, HCl? I'll give you guys a second. Yes, so HBr is going to be more acidic because Br minus is more stable than Cl minus because Br minus is bigger. And the bigger of an atom you are, the better you take a negative charge. The same thing applies here. So the bigger our leaving group, the better it is. So for example, iodine is the best leaving group and fluorine is the worst leaving group. So iodine is the best, followed by bromine, followed by chlorine, and finally fluorine. Okay? So the bigger our leaving group, the faster our reaction will go. And this is both for Sn1 and for Sn2. Okay? Does that make sense to everybody?
Can you please repeat that again? I couldn't hear
So
this coming up.
the bigger our leaving group, the better the leaving group, the faster our reaction will go. So since iodine is our biggest halogen, that's going to have it's going to be the best leaving group and it's going to do the best it's going to do the fastest reaction when compared with bromine and Cl. And you can see here that sort of feeds into the ideas of acid strength. Okay? Does everybody make sense so far? Is the leaving group the same for all reactions? Yes. So the leaving group trend will be the same for Sn1 and Sn2. That's why I came to it last. So good leaving groups are weaker bases? Yes. 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 All right. So, I think I've gone over everything for Sn1 and Sn2. So we will do some example problems. So I'm going to pause the recording here, and then when I start it again, I should have some example problems written out. I actually forgot something to mention, so I'm actually going to go over that now. We're going to compare Sn1 and Sn2 overall with the same type of nucleophile. Sorry, guys, I faked you out, but then we'll do example problems. So let's say that we have this guy here and this guy here. So these are the same types of alkyl halides. They're both secondary. So if they're going to be Sn1 or Sn2, depends on the nucleophile and the solvent. Right now, we're just going to focus on the nucleophile. So for this top one, we're going to say this nucleophile is going to be OCH3. For the bottom, we're going to say it's HOCH3. Obviously, this top one has the stronger nucleophile. So this is going to be a Sn2 reaction, whereas the one on the bottom is going to be Sn1. So let's do the Sn2 reaction mechanism first. Obviously, the leaving group is going to leave, and at the same time, we're going to do our nucleophilic attack. So what happens here is our leaving group leaves, and here's our nucleophilic attack. Okay? And so then we just end up with a single product with inversion of stereochemistry, and you can write it like this to replace, so to represent OCH. This is OCH3, okay? So now this bottom one is going to be Sn1. So we all know that the first step of Sn1 is the leaving group leaves. So let's label that leaving group leaves. So now we're at the carbocation. So let's pause here. Let's do like a big pause here. That's supposed to be a pause symbol. So when we have our carbocation, we can undergo something called a carbocation shift. This cannot happen with Sn2 because Sn2 does not do carbocations. Whenever we have a carbocation, we can undergo some sort of carbocation shift. Right now, as far as we know, the only thing that can undergo a carbocation shift is going to be this Sn1 reaction. So what happens in a carbocation shift? Well, the idea of a carbocation shift is if we have a carbocation next to something that would make for a more stable carbocation. So for example, we have a secondary carbocation here next to a tertiary carbon right here. All right? Does that make sense to everybody so far? So this is not the same carbocation. I'm just making this up as I go. So in this case, we have a carbocation that's next to a tertiary carbon. So what happens here, this is going to be a rearrangement. What happens here is we're going to want to shift something. We're going to want to shift either a hydrogen or a methyl in order to make a more stable carbocation. And this can only occur between adjacent carbons, okay? So if I had something like this, I wouldn't be able to do any shifts because the tertiary carbon is too far away, all right? So let me erase this. So usually what will occur is something called a hydride shift. So when our carbon that is more stable has an extra hydrogen, it will basically donate this hydrogen to that carbon there. Then we end up with a hydrogen right here, and our positive charge kind of moves. And let me draw this out with the with a sort of semi-Lewis structure here. So let's compare the two of these. So this one on the left, this will represent our tertiary carbon. Oh, sorry, that shouldn't have the positive charge. And this one on the right will represent our secondary charge. So what will occur is basically what happens is this hydrogen bond sort of hops over to that positively charged carbon. And so then we end up with this guy right here. So remember, carbocations will have 3 electron groups. So you can see here that when the hydrogen bond sort of hopped over, we ended up with this guy on the left now having the positive charge. That's how the positive charge moves. We're not actually moving the positive charge, more so we're moving a hydrogen bond, okay? This is a hydride shift because we're moving a hydrogen. Most of the time we'll have a hydride shift. The time, again, I call this, or everybody calls this, a 1-2 hydride shift because the 1-2 sort of represents the carbons being right next to each other, where we're moving from carbon 1 to carbon 2. Sometimes we'll do a methyl shift. A methyl shift occurs if we have 0 hydrogens to donate. So that would be, for example, if instead of being a tertiary carbon here, we had a quaternary carbon. Okay? So what occurs here is we move a whole methyl group rather than just a hydrogen. Okay? The reason why we'll usually do hydride shift is because they're easier. Hydrogens are smaller, they're easier to move around. Okay? So usually it's either going to be one or the other. Most of the time it will be a hydride shift, but if you have a quaternary carbon, it'll end up being a methyl shift. And again, this rearrangement can only occur when we have carbocations. So this can only occur in Sn1 rather than Sn2. Okay? Does that make sense to everybody? Okay, awesome. So let's say that we had this alkyl halide here. So let's say like we had both alkyl halides here. So you can see here that, so let me erase all this extra stuff here. Where's my eraser? Right here. So I'll just use this bottom bit to show the hydride shift. So yes, this carbocation rearrangement will also occur with E1, but we haven't exactly gotten there yet. So we will talk about that, okay? So you can see here that this carbocation will undergo a carbocation shift. Yeah, so let's erase this really quickly. So now we can see that when we do Sn1, what will occur is we will get, also, I'm just going to draw the Sn1 product as a line because it saves room. But know in your mind that Sn1 will have both enantiomers. But right now I'm not drawing it because I'll run out of room. But now we have this guy right here. And so now we know our Sn1 reaction is done. This is where Sn1 reaction ends. This is where the nucleophilic attack occurs. So I'm going to have OCH3. It'll attack here. This is our nucleophilic attack. So this is the end of Sn1, but this is not the end of our reaction. So usually what will occur is our leaving group, so Cl negative, will come in and it will deprotonate. Let me use my color for my arrows. It will come and deprotonate this guy right here. And we call this a proton transfer. Okay? So this step here is a proton transfer. This is also a proton transfer. We just call it a 1-2 hydride shift because it kind of has a special name. Okay? And so then we end up with our final product that looks like this. And we can also say that this will end up with both enantiomers, but in this case, it doesn't matter because this is not a stereogenic center. So we could just draw this guy out and be correct. Okay, and this is not a stereogenic center because this side and this side are the exact same group. And why does this proton transfer at the end have to happen? Well, basically it has to happen in order to make this stable product. This product right here is not stable, so it spontaneously transfers a proton to become the most stable it can be. Okay? So we can see here, Sn2 is very simple. All we do is a leaving group leaving and a nucleophilic attack. Whereas Sn1, we can have our leaving group leave, we can have a proton transfer, we have a nucleophilic attack, followed by another proton transfer. So Sn1 is the more complicated version. So just keep in mind, proton transfer occurs at almost every end of Sn1 reaction. Because again, remember, Sn1 will use the weak nucleophile, which usually has a hydrogen to sort of get rid of its negative charge. So a lot of the time, 90% of the time, you're going to do a proton transfer at the end of your Sn1 reaction. Okay? All right, so I think I've covered everything for Sn1, Sn2, and now I can do the practice problems. So give me a moment to write those. Oh, go ahead.
Could you use the OCH3 to deprotonate instead?
Yeah, you like a lot of the time you'll see this as your deprotonator, but you could also see another like molecule of your nucleophile doing the deprotonation. It just depends on what the question is asking. Okay?
Okay. All right. Thank you.
All right.
I have
All
a
right, so
question.
go ahead.
I know in Sn1 there's 2 different steps. Where would the first step be in like the example you have up, in the second
All right. So the first step is when the leaving group leaves. This is our slow step. The second step is when our nucleophile attacks. This is our fast step. Again, this proton transfer step isn't technically a part of the Sn1 reaction. It's just there because it usually spontaneously happens without our intervention. Okay? Does that make sense?
Yes, thank you.
Okay, awesome. All right, so now I'm going to pause the recording and I'll have a bunch of practice questions written magically. All right, so I wrote out a few of these problems for you guys. I'll give you guys in the live chat. I'll give you guys a few minutes to try and work them out yourself. If you can't, that's totally fine. And then if you're on the YouTube video, just pause it and try to work these out yourselves. You can see that I've numbered them. So for example, 1 is just going to be tell me the product of this reaction. 2 is if we use a solvent with this very same reaction, assuming that it will stay Sn1 or Sn2, will this cause the reaction to go faster or slower? And then 3, again, same idea. So 4 and 5 are just figure it out if it's Sn1 or Sn2, and then write down the product. 6, which leaving group is better, which one will cause it to go faster. 7, just write the product. 8, we have the solvent and the nucleophile being this ethanol, which is an alcohol. And so then you can figure out what kind of reaction it is using this solvent and this nucleophile, and then you can tell me the answer. 9 and 10, I'm going to have you tell me, or I guess tell yourself because you can't really tell me, which products will be formed if we use like this as our nucleophile. So like 9 is if I use OH as my nucleophile, you would say, oh, I'm going to get like 4 and 5 or whatever. Of course, 4 and 5 aren't an option. 10 is the same thing. You're just going to tell me different numbers. All right, so go off and do it. I believe in you. All right, so now somebody asked if there aren't any dashes or wedges for Sn1s. Yeah, you can't have any enantiomers because there's no stereogenic center. So back to this. So I'm just going to write down it's not necessary to have a hydride shift in every Sn1 reaction. It just occurs when you have a more stable carbocation available. So what I'm going to do here is I'm going to clear my screen. I have the questions, like I took a picture. I'm going to explain the process of each of them, but I'm just going to write the answers because I kind of want to be done in an hour so I can study for my own test. But anyways, all right, so I'm going to clear these. So question number 1, we had a primary alkyl halide with a strong nucleophile. That means we're going to have Sn2. And since we don't have really a stereogenic center there, we aren't really going to worry about it. We're just going to call it this. Okay? For the second question, it asks, okay, if we used H2O as a solvent, will this make the reaction faster or slower? Again, this is an Sn2 reaction. H2O is a polar protic solvent. Sn2 does not like, oh yeah, you can also include Cl- over here. I just didn't because it's less important. And remember, we used OH minus, which means it's going to be a strong nucleophile, so it's going to be Sn2. Okay, so again, Sn2, it does not like polar protic solvents. We're going to assume that, this reaction here is Sn2. We know H2O likes Sn1 reactions, but we are going to assume that we're going to keep the Sn2 reaction because we have a strong nucleophile and a primary primary alkyl halide. So that sort of overcomes the H2O. But again, Sn2 does not like H2O, so this is going to cause the reaction to go slower. Same idea with number 3, acetone. Acetone, I'm sure you either Googled it or I told you, looks like this. This is polar aprotic. Sn2 loves polar aprotic, so this will cause the reaction to go faster. Okay, so what happened here is we kept Sn2 for each one of these steps. It's just 2 had a factor that made the reaction go slower, and 3 had a factor that made the reaction go faster. And that's the big difference here. Apologies if I kind of go through these fast. Again, I kind of want to get to E1 and E2, and I've already been here for 2 hours. So, all right, so 4. We have a secondary alkyl halide and a strong nucleophile. That means we are going to do Sn2. And we know Sn2 only does inversion of stereochemistry. So this is the only, I just wrote I. This is the only product we end up with along with I minus. Okay? All right, so number 5. Again, we have the same exact substrate, but now we're using H2O. So again, we're going to end up with both enantiomers. And again, remember, we're going to end up with this product for the Sn1 reaction, but because that Sn1 is followed by a deprotonation immediately by iodine, we're just going to write this product here along with its enantiomer. Okay? And then also with HI, because iodine did the deprotonation, so we end up with HI. Of course, these 2 products are generally more important, and they're probably what's going to be asked about. Okay, so 6, it's asking which reaction is faster, one where the leaving group is iodine, and one where the, go ahead.
So the one we just did was Sn1, right? Just to make
Yes.
sure. Okay, perfect.
And this makes a racemic mixture. Because again, these are enantiomers because we don't have another stereogenic center. Okay, back to 6. So it's comparing iodine as a leaving group and chlorine as a leaving group. Somebody said, so the final answer on the exam would have OH attached, not H2O. Yes, exactly. Because generally with Sn1 reactions, the deprotonation happens spontaneously. It happens without us having to do anything. So we just assume that it happens, and that's going to be our final product. Okay, back to 6 again. So again, this is comparing leaving groups. Iodine is a bigger leaving group than Cl. Yeah, 5 is Sn1 because we had a weak nucleophile. Deprotonation is removing 1 hydrogen exactly. All right, back to 6. So somebody asked, since we're using H2O with number 5, why isn't it Sn2? Because H2O is a weak nucleophile, so we are going to do Sn1 over Sn2. Okay, does that answer your question? All right, awesome. So back to 6 again. It's okay. I'd rather answer your questions now than have you confused on the test. So that's good. So anyways, 6 is comparing our leaving groups. Again, iodine is bigger than chlorine, so it's going to be the bigger leaving group, and thus its reaction is going to proceed faster. All right. So 7's kind of easy, because we have a tertiary alkyl halide and a weak nucleophile. So it has to be Sn1. And again, I'm going to write the final Sn1 product or after deprotonation, because that happens spontaneously. And again, you can see here that I did not write any stereochemistry for this carbon, because this carbon is not a stereogenic center, so it's not as important. Because you can see here that this CH3 group and this CH3 group are the exact same. Okay? All right. So 8 had OH or ethanol as both our solvent and our nucleophile, okay? So basically what happened is, since it's our solvent and our nucleophile, we have a protic solvent and a weak nucleophile. That means we're definitely going to be doing Sn1. So that means we're going to end up with two products post deprotonation. Again, I'm writing the deprotonation. I'm not writing the deprotonation step, rather, because it's going to be just make it a little faster for me. Okay, so then we end up with two products. So these, oops, there should be an oxygen there that I just did not write. These can be considered enantiomers only because this group here, I did not give stereochemistry. If it did have stereochemistry, like if they were solid wedges, then we would consider these diastereomers. Okay? Why? Oh my goodness! You guys just caught me. It should be a rearrangement. I'm going too fast for my own good. You totally caught me. So again, yes, it would be a rearrangement. Thank you for pointing that out. Because what would happen here is we have a carbocation, a secondary carbocation, next to a tertiary carbon. So then you can do a carbocation shift. I think you guys can tell I've been kind of doing this for 3 hours. So our carbocation would end up right here. And again, we would end up with both products, both enantiomeric products, one that looks like this and one that looks like, so sorry about that. I totally slipped right here. I hope you still like me as a TA. Boo-hoo, I'm going to cry. So this would be the product of number 8. So sorry for that issue. But yes, there would be a shift. All right, so 9 is now where we get into sort of the nitty gritty. So 9, we start out with a secondary, the line becomes a wedge. Yes, because remember, back to 8, sorry. Remember when we make our carbocation, that's going to be trigonal planar. So no matter what, it's going to be a line. So when we add our nucleophile, it's either going to add front side or back side attack. And as a result, we're going to have both possible products. Okay? Does that make sense? I hope it does. Okay, awesome. So 9 and 10, they're sort of pick the ones that will work with this. So we have a secondary alkyl halide with a strong nucleophile. So we know that when we have a strong nucleophile with a secondary alkyl halide, we are going to do Sn2, which means we are also not going to do any type of rearrangement, and we're going to end up with inversion of stereochemistry. So the ones that did not do any rearrangement were 1 and 3. However, 3 has retention of stereochemistry, so that means it cannot be the answer, and 1 is our only answer. Oh, I just got a message that my internet connection is unstable, so sorry if it kind of glitches in and out.
Wait, so why isn't 3 one of them? Can we see
Because remember, Sn2 only does inversion of stereochemistry. It does not do retention of stereochemistry, so it has to be 1 and not 3. Okay? Does that answer your question?
Yeah, thank you.
Okay, awesome. So now 10 is now using H2O instead of OH. So that means it's Sn2 because of the OH, right? Yes, because OH negative is a strong nucleophile. So Sn2 only does inversion. It does not do retention. Sn1 does both inversion and retention. So now 10, we're using H2O, which is our weak nucleophile in conjunction with a secondary alkyl halide. As a result, now we're going to be doing Sn1, which means we're going to do both a possible carbocation rearrangement where we have, we start with this carbocation next to a tertiary carbon. So we'll undergo rearrangement. And then we'll also do inversion and retention of stereochemistry. So that means that both 2 and 4, which both undergo rearrangements, can be our answer because it has both enantiomers. Okay? Does that make sense? All right, I hope that going through these practice questions helped you with Sn1 versus Sn2. So now we will be doing E1 and E2. Yay! E1 and E2 are fun. All right. All right, so now we are going to go into E1 and E2. And now that you know Sn1 and Sn2, this E1, E2 stuff should be at least a little bit easier. Yes, and also, just so you guys know, I have cheat sheets, quote unquote, for Sn1, Sn2, E1, E2, and then how to tell if a reaction will be Sn1, Sn2, E1, or E2. I will put those in a Google Drive and link it in the description of the video on YouTube. And I'll also send it to everybody in the live chat right now. All right. All right. So now let's talk about E1 and E2. So let's talk about elimination as a whole. So when we talk about elimination, we call it alpha beta elimination. So alpha beta elimination. And there is a reason we call it that. So when we do alpha beta elimination, it's the idea that we're going to have an alkyl halide once again. We'll just have chlorine as our alkyl halide. The carbon that is directly attached to our halogen, we're going to call it our alpha carbon. The carbons that are attached to that alpha carbon, we're going to call our beta carbons, okay? And so generally what occurs is that the alpha carbon will have its halogen removed, eliminated, and one of the beta carbons will have its hydrogens removed. So we'll call this one beta 1 and we'll call this one beta 2. So if we undergo elimination using beta 1, we will eliminate this hydrogen and we will end up with this product here. So we can see here that a double bond was formed between our alpha carbon and our beta 1 carbon. On the other hand, if we use beta 2, we use beta 2, then we will eliminate the hydrogen on beta 2 and we will end up with this product where our alpha carbon is here and our beta carbon is here. So you can see here that for both of these, our double bond touches the alpha carbon. It has to. And then it can either be beta carbon 1 or beta carbon 2. All right? So the idea behind elimination is we eliminate both a halogen and a hydrogen. Okay? So we eliminate two things to make a new double bond. Okay? So let's talk about the Zeitstev and the Hoffman product in between of these. So the idea of a double bond is a double bond will have a certain stability. So when we talk about a double bond, we're going to highlight the full double bond. So let's highlight the full double bond here. And then we're going to count how many carbon substituents it has attached to it. So it's the same sort of thing as when we did the carbocation, is we're going to count and see how many substituents are attached to our double bond. So in this case, for 1, we are going to have 1 substituent here and 1 substituent here. That makes this have 2 substituents. We're calling it a di-substituted alkene, okay? Whereas this bottom one here, this bottom one only has the single substituent on this side, so we're going to call it mono-substituted. We can have more substituents, like for example, this top one had another substituent right here. We would call it tri-substituted, and then if it had another one right here, we would call it tetra-substituted. Oh, sorry, somebody said it cut out. But we can see here that at 1 has 2 substituents, so we're going to call it di-substituted. Product 2 has 1 substituent, so we call it di-substituted. And we can continue adding on more substituents. Like for example, if I added a substituent here, this would be tri-substituted because it has 3 substituents. Or we can add another one here, and that would be tetra-substituted because it has 4 substituents. Okay? Does that make sense so far? Okay, awesome. So the more substituted your double bond is, the more stable it is. So product 1 is more stable than product 2, okay? And we call our more stable product, we're going to call it our Zeitstev product. Forgive me if I spell it wrong. we're going to call our less stable product the Hofmann product. Okay? I don't really have a name to memorize these. Just know more stable is Zeitstep, less stable is Hofmann. Okay? Or I guess more substituted is Zeitstep, less substituted is Hofmann. But I digress. Okay? So most of the time, we are going to make more of the Zeitstep and more stable product. Thus, we will call this product our major product. And then we will call the other product the minor product. Okay? But again, these minor products can swap depending on a couple of factors. But in general, if you're using a smaller base, it's going to be assumed that it will be the more stable product will be the major product. Okay? Are you with me so far? Okay. Sometimes, however, this second product can become the major product. And this occurs when we have very big, very bulky bases. So let me erase this here and make it a little bit more clear. So let's think of these hydrogens as parking spaces. This beta hydrogen here, this beta hydrogen is a better parking space. It's closer to the doors. It's on the first floor of parking garage H. Whereas this one right here, this is a bigger parking space, but it's less preferred. It's like on the top floor of a parking garage, is way away from the doors. If we have a tiny little baby base, yes, the idea is more substituted means it means more stable. Sorry. So if we have a tiny base, this should be as if we had like a little tiny baby bug car, a little bug car that can fit into basically any parking space. So it can fit into this more stable, more substituted hydrogen. However, if we have a very big and bulky base, that would be something that looks like this or something, it cannot fit into that small base. It's as if we have like a big truck to show everybody how tough I am. It can't fit into that small parking space. So it has to go over to this bigger parking space here and make the Hofmann product. How did you determine which hydrogen was bigger? Well, the less substituted hydrogen has the bigger parking space, okay? So that means that when we have a bigger space, the big base has to fit into the less substituted hydrogen, which thus makes the Hofmann product our major product. Okay? Does that make sense so far? So small bases will make the Zeitstep product. Big and bulky bases will make the Hofmann product. Okay? And so that is why it sort of depends on which kind of base that you use in order to select which region you'll remove a hydrogen from, which makes these reactions regioselective. This base is sterically hindered. It's big and bulky, it's sterically hindered. One more thing that we should talk about here is this is a strong base. And usually strong bases are also strong nucleophiles. I'll get back to the regioselective portion in just a second. I just want to finish this idea. Usually strong bases are also strong nucleophiles. Like OH is both a strong base and a strong nucleophile. But when we are very sterically hindered, we cannot be a strong nucleophile, and instead we will be a strong base, but a weak nucleophile. Okay? Does that make sense? And these strong bases, weak nucleophiles, normally will not do Sn1 or Sn2. All right. So when I said regioselective, I was saying these bases sort of determine what region the double bond will be added to. So these bases cause the elimination product to be regioselective. So a sterically hindered base will contribute to a Hofmann product, and a small base will contribute to a Zeitstep product. Exactly. Okay? So if we have a big sterically hindered base, then our Hofmann product will be our major product, and our Zeitstep product will be our minor product. Okay? Does that make sense so far? Okay, awesome. So that is honestly basically the long and short of it of E1 and E2, or elimination as a whole. So let's talk about E1 and E2. So E1 and E2 are very similar to Sn1 and Sn2. E2, everything occurs in a single step. So we have our base here. Our base will grab our hydrogen. I'm just going to draw one product here. I'm going to draw the Zeitstep product, but know that both products can form. I'm just going to draw both of them, or I'm just going to draw one of them here to save space. So essentially what happens is our chlorine is going to leave. Our leaving group leaves, and instead of attacking the carbon that the halogen used to be attached to, the base will attack the hydrogen. And again, hydrogen can only hold onto 2 electrons at a time. And as a result, this bond has to break, and it will create the new double bond. And so then we end up with our elimination product here. For E1, however, similar to Sn1, we are going to create a carbocation. Okay, so our leaving group will leave first, and then we'll create our carbocation, and then our base will take the hydrogen. Ooh, let me draw it this way. Then our base will take the hydrogen, and we will end up with our final elimination product. Okay, does that make sense? Again, you'll have both the major and the minor product. I'm just showing the mechanism for the more stable product. So yes, for E1, you can see that we have this carbocation. Whenever we have a carbocation, we can do some sort of hydride shift. So because we have this carbocation, we can undergo a hydride shift. It's just in this case, we didn't have to do any. Okay? Does that make sense so far? Okay, awesome. So like for example, if instead of having that carbocation, we had this carbocation, again, we will undergo some sort of shift, and then our elimination product will move. And then we would end up with these 2 elimination products, this one here and this one here. If we, again, there's a third beta carbon here, but it makes the exact same product as this one here. Okay? Does that make sense? How do we know when to add a shift again? You know to do a hydride or a methyl shift whenever you have a carbocation that has a positive charge next to a more substituted carbon. Okay? How many products can you have in E1? You can have as many products as there are beta carbons. So like for example, if this is our alpha carbon, we have 1, 2, 3 beta carbons. So that means we can have 3 products. It's just sometimes these different beta carbons can come up with the same exact product, and you'll end up with only 2 products. Okay? Does that make sense so far? All right. So honestly, that is the biggest difference between E1 and E2. It's honestly not as complicated as Sn1 and Sn2. The big difference between E1 and E2 is you have that that carbocation, which can undergo a shift. Okay? All right. So let us clear this very quickly, and we'll talk about the differences between E1 and E2. So we talked about the differences in products. The main difference is the E1 product can have some sort of, somebody said, would the tri-substituted product be more stable than the tertiary car? Yes, the tri-substituted double bond will be more stable than the di-substituted double bond. All right, so let's talk about how to tell if something's gonna be E1 or E2. Similar to Sn1 and Sn2, E1 prefers weak bases, because again, it wants to give the leaving group time to leave and create a carbocation. This is like as if we were using H2O. E2 prefers strong bases because again, it wants to occur as fast as possible, so it's going to use something like OH negative. Okay? Now, this is where E1 and E2 majorly differ from Sn1 and Sn2. E1 and E2 both prefer tertiary over secondary over primary over methyl. They both prefer this because of their transition states. So E1, the transition state E1 makes sense because we want to make the more stable carbocation. So again, we're following the same rules as Sn1. We prefer a tertiary carbocation over a secondary over a primary, and et cetera, et cetera. E2 is a little less clear. So let's say that I had this guy here and this guy here. Both of these will undergo elimination reactions. The transition state, however, will be slightly different. So this one will have a transition state here, partial positive on the carbon, transition state here, partial negative on this carbon, and then like a partial double bond. Okay? And the reason why this is partially negative is because the hydrogen is being taken away. The hydrogen is being taken away, so that carbon is going to take the rest of those electrons. So that means that it has to be partially negative. So now let's compare this one here. So this is going to be partially positive. Again, this one will be partially negative. We end up with a hydrogen here and a partial double bond. Okay? Does this make sense so far? So we can see here that this one, this secondary alkyl halide, will have the more stable transition state than the primary alkyl halide. As a result, because this transition state is more stable, the whole reaction will be more stable overall, and we will prefer tertiary over secondary over primary. Okay? Does that make sense? That is why E2 prefers tertiary over secondary over primary, because it doesn't have to worry about steric hindrance, but it does have to worry about a more stable transition state. Okay? And those are the major differences between E1 and E2. We don't really have to worry about protic versus aprotic solvents as far as E1 and E2 go, because they don't really care as much about separating out a nucleophile and a alkyl halide. They're more about making an acid-base reaction. Okay? So these are the main differences between E1 and E2. Now, something you may note, these strong and weak bases are very similar to our tertiary is more stable for E2 as a more stable transition state. You may be noticing that our weak bases and our strong bases are very similar to our weak nucleophiles and our strong nucleophiles. And you would be right. So a lot of the times, E1, E2 can occur at the same time as Sn1 and Sn2. How to separate the two of them? You can sometimes use heat. For example, if you use heat with an E1 plus Sn1 reaction, you can force it to prefer the elimination reaction. So when you see heat, it's going to prefer the elimination reaction. For E2, we can force it to do the elimination reaction by using a strong base that also happens to be a bad nucleophile like we mentioned before. So like, for example, this is a strong base, weak nucleophile. It will prefer elimination, E2, as well as the Hoffman product. Okay? Does that make sense? So that's why we can force E2 to happen more than Sn2 by using a bulky base, because bulky base this can be a strong base but a weak nucleophile. Let me move the chat so I can write down. Strong base, weak nucleophile. And remember, Sn2 needs a strong base. I mean, sorry, not a strong base, but a strong nucleophile. E2 just needs a strong base. So if we have a strong, bulky base, a strong base, weak nucleophile, that means we're going to do E2, and we're also going to be doing the Hoffman reaction as more as the more the major product. Sorry, I had a brain fart there. So all bulky bases are E2. Generally, yes. We're gonna focus more on bulky strong bases being E2 rather than having bulky weak bases. For having a reaction that can have both substitution and elimination, you should write all of the reactants. Hopefully, you won't really have to on the test since it's multiple choice and fill in the blank, but just be aware that if you have both Sn1 and E1 occurring, unless it asks for only the major product, you have to write out all of the all of the products, sorry. So the way that you can differentiate between E1 versus Sn1 is through heat, which will probably be shown as a triangle, E2 versus Sn2 by using a bulky base. Okay? One more thing to note about Sn1 versus E1. Sn1 and E1 almost always occur together unless you use heat. This is because they use the exact same weak base, weak nucleophile, as well as they have that carbocation intermediate. The carbocation intermediate doesn't really discern between whether we're going to be doing Sn1 or E1 unless we have heat sort of energizing this hydrogen molecule here, which then sort of prefers E1. If you have E1 and Sn1, you will probably have four products. So let's do an example like that. So let's say that we have this guy here, Cl, and we have H2O. This can be both the solvent and the nucleophile, or it can just be just the nucleophile and we have a different solvent. But right now we're just focusing on H2O. So we know that this is going to be Sn1 and E1. So Sn1 will draw our products as two enantiomers. Like this. Oops, that should not be a Cl, that should be an OH. Again, I'm skipping the deprotonation step just to save time. For the E1 reaction, we'll say, okay, here's our alpha carbon. We have beta 1 here and beta 2 here. Beta 2 here is going to be our major product because it's more stable. And beta 1 here will be our minor product. Okay? And so again, there's no real major versus minor product with Sn1 versus Sn1 products, just because we assume that they're created about equally, whereas with E1, the more stable one will be our major product as far as we're using a small base, okay? All right, so in this case, we would get 4 total products. Hold on, so let's do a different possibility. So let's say that instead of using H2O, so instead of getting these products, we get, we use OH negative. Now we're going to be doing both Sn2 and E2. So now again, we'll draw the products. Sn2 only creates one enantiomer, so we end up with this. E2 will create both of these guys. It's just, again, since we're using a small base, this is going to be major. So we said, what if there are 2 bases, one above and one below the arrow? Usually what that means is the one above the arrow is going to be our nucleophile or our base, and whatever is below the arrow will usually be our solvent. Okay? So when something has a strong base and a strong nucleophile, both Sn2 and E2 products will be present. And when something that is both a weak base and a weak nucleophile, Sn1 and E1 will be present. Exactly. So the only time we'll only have like one of those products is if we're using a strong, bulky base. So let's say we're using this guy right here. You may hear this referred to as you may see this referred to as like CH2, CH3, 3O negative, or maybe you'll see CH3, 3O negative. All of these are strong, bulky bases that are not good nucleophiles. In this case, we will only be doing E2 because this is a strong base, weak nucleophile. So we end up with, again, the Hoffman product as our major product. Oops, sorry. Yeah, major product because this is a really big base. It's got to go to that big parking place. And then we have this minor product right here, which is the Zeitstep product. Okay? Let me share something very quickly that sort of breaks down E1 versus E2 versus Sn1 versus Sn2. The only thing that this document it is lacking is, I'm about to share it, is the factor of heat. But again, if we use heat, then it's going to prefer elimination. Okay? So again, I'm going to share this with you guys, either through the description of the actual YouTube video, or through, or I'll just send it to you directly with the live chat. Okay? If it wasn't heat, if there was no heat, then you're just going to assume that everything will occur. Sn1 and E1, Sn2 and E2. Okay? All right. So this is generally what you'll need to know as far as alkyl halides, linear alkyl halides go. Elimination, Sn1 and Sn2. Are there any questions? What's another common bulky base that isn't tert-butyl? There's nothing coming up at the top of my head. Just sort of know that if you have like something that's like negatively charged with a bunch of stuff coming off of it, that's usually going to be a bulky base. Okay? But most of the time you'll probably see tert-butyl. Okay? Oh, sorry. No. Sorry. Yeah. No. Sorry. Again, I'm going to share that document that I had up a second ago with you guys. Like, I'm going to share this whole thing with you, so you don't have to write it down if you don't want to. Again, I have guides for Sn1, Sn2, E1, and E2 that I'll also send to you guys, either in the description or just in the live chat. All right. Well, let's go back to the whiteboard. And all right, so I'm just going to go over what makes Hofmann the major product just one more time. So the idea is, so I'm going to draw this a little bit bigger. The idea is we have our alpha carbon here, and then we have beta 2 and beta 1 here. Beta 2 is more sterically hindered than beta 1, but eliminating from beta 2 will make a more stable product. So when we use a small base that's not going to be worried about steric hindrance, it can easily grab this hydrogen and make the Zeitstadt product. However, if we have a bigger base, that's going to worry a lot more about steric hindrance. And so it's only going to be able to attack this less sterically hindered hydrogen and then cause the Hofmann product to form. Okay? Does that clear up some of those questions? All right. So now let's talk about everybody's favorite section in this chapter. I'm being sarcastic. The anti-periplanar idea. So if you remember, whenever we have cyclohexanes, we have to draw them in this wonderful thing called the chair conformation, which everybody hates. And again, just a reminder, each carbon of the chair conformation will either have an up or down substituent or an axial and equatorial substituent. So let's say that we have a chlorine right here. That means that on this one, if I want to make that solid wedge go down, then it's going to be down axial. If I want to make that wedge go up, it's going to have to be up equatorial. Okay, does that just like a quick refresher for everybody about not anti-periplanar, but about the idea of the chair conformation. Sorry, I blanked there for a second. All right. So the idea here is that, okay, so if I have a chlorine on a solid wedge here, I also have, I don't know, an OH on a solid wedge right here, that means the chlorine will be pointed, let's say they're pointing up, I guess, if we're on the solid wedge. Cl will be up, and the OH will also be up because they're both on solid wedges, so they have to be pointed the same direction. If I wanted to, I could also make them both point down. I just tend to make solid wedges point up just so like I can stay the same with everything, but it's just whatever preference you have. All right, so the idea behind the anti-periplanar sentiment in elimination is that whenever we have a cyclohexane, we have to have a hydrogen in the exact opposite plane to do an elimination reaction. So what I mean by that is, let's say we have a hydrogen here and a hydrogen here. If I just drew these on my sorry, let me draw these with actual wedges and stuff. So if I drew these on my my cyclohexane, it would look something like this. Okay? So you can see here that the blue hydrogen is sort of opposite to the chlorine, it's sort of trans the chlorine. And so what we have to do for elimination is we have to have a hydrogen in the opposite direction, axial, with the leaving group. So this example, chlorine is axial down. So to eliminate, the corresponding hydrogen has to be axial up. Okay? Does that make sense so far? If I had my chlorine equatorial up and my hydrogen, I don't know, equatorial down, we can't do that elimination. We have to have them in the axial position. Okay? But what's more important is they sort of have to be trans to each other. They have to be pointed in opposite directions. So for example, if I had, let's say that I had a, let me use a different color. Let's say I had just a methyl group right here. If I did an elimination reaction and I ask you what is going to be the major product, and I'm using a small, strong base, you may be tempted to tell me my final product will end up being this, because this would create the Zeitstep product, the more stable double bond. And somebody said leaving groups always have to be axial. Yeah, when we're doing elimination, when we're doing elimination as far as cyclohexanes go, you want to make the leaving group axial. And so again, you may be tempted to say this is our major product because we're using a small, strong base, and that small, strong base will make the Zeitstep product. You would be wrong because when we draw in that methyl group on our chair conformation, we can see here that that carbon now has 0 anti-periplanar hydrogens. So we cannot make a double bond right there. So we have to make the double bond, we have to make the Hoffman product, okay? Does that make sense? And that is basically the gist of anti-periplanar elimination as far as cyclohexanes go. The Zeitstep product, generally it won't really, it would be like very, very minor. But most of the time, this question would be like, please select the major product, and you would have to select this one. Because even though it's the Hoffman product, because of the anti-periplanar rule, we have to make the Hoffman product our major product. Okay? Does that clear up anti-periplanar? So cyclohexanes, well, not always. You'll use this anti-periplanar rule when you're using cyclohexanes. So the idea is our leaving group has to be trans to one of the hydrogens. So like, for example, if instead of being a dashed wedge here, this methyl group was a solid wedge, and our hydrogen was on the dashed wedge, then we could make the Zeitstep product. But the way that I drew it the first time, we could not make that product. Okay? Does that make sense? To do an elimination with a hydrogen on a cyclohexane, that hydrogen has to be trans to our leaving group. So if our leaving group is on a solid wedge, the hydrogen has to be on a dashed wedge. If our leaving group is on a dashed wedge, our hydrogens have to be on a solid wedge. Yes. All right. So that's periplanar, anti-periplanar idea. It's honestly far easier than it seems to be, but it has to do with the so would you keep the methyl on a wedge? Yeah, you would. I was lazy. Fine, I'll draw it in. The general rule for this is because we want the base to not have as much steric hindrance. So the base can sort of do a drive-by when it's in the axial position. It can't really do that as much when it's in the equatorial position, okay? The major product would be Hoffman if it was a strong, bulky base. Yep. If we have a strong, bulky base, it's always going to be the Hoffman product. Okay. So does that clear up? I'm not sure what you're asking about the rotation around a single bond with only one beta carbon, but all right. All right, so now I'm going to do what I did before. And I'm going to write up some E1, E2 questions. Some of these may overlap with Sn1 and Sn2, but focus more on the E1, E2 portions. All right, so I went ahead and wrote out these questions for you guys. If you're on YouTube, then just pause the video and just work them out. If you're in the live chat, then just take your time to do them, and I'll see you in a second. Just occurred to me that I just completely forgot to write the base here. But again, assume for all except for 7 and 8 that we're just asking for the elimination product. Okay? Just assume. All right. All right, so I've given everybody time to go over all of these questions. Again, I'm just going to write the answer in order to sort of keep things moving here. Again, what I'm asking for right now are the elimination products. But if you wanted to write the substitution products, you could, and that would be probably helpful for you. But anyways, so I'm going to clear this. So question 1. So question 1, basically we start out with our final alkene. So here's our final alkene. And so there are here's like our alkene without a double bond. So there are basically 2 possibilities here. One where our alpha carbon is here and our beta carbon is here. And oops, it got rid of this one. And one where our alpha carbon is here and our beta carbon is here. But again, it wasn't asking for the major product. It was asking for, it wasn't asking for the ones that would only make that that alkene as a product. It was asking for any of the alkyl halides would make the product. So yes, these are practiced for E1 and E2. And so then we can write these as, this has our X group on it, which is just our leaving group. And this one has an X group right here. What's important to note here is that this second one is the only one that would only make that product. If it was asking you what reactant will only make this product, then this would be the answer. But I asked which of the alkyl halides, or write me an alkyl halide that can make the product. So both these answers would be correct. So number 2, so we're using H2O and our alkyl halide. Again, this would be Sn1 and E1, but I'm focusing only on E1 right now because we used a weak base, okay? So that means that we'd get a rearrangement. So our plus charge would end up right here, which means our 2 products would look like this and look like this. And our major product would be this one right here. All right? For 3, it's basically the same thing, except now we're using a strong base. Again, this would also be Sn2, but for right now, we're just focusing on elimination. So elimination, we have 0 rearrangements. So our 2 products would look like this and this. This would be our major product, and this would be our minor product. So now we come to 4. And now we see that it has a bulky base and a strong bulky base and a weak nucleophile. Oh, for 3, what's important to note is that yes, stereochemistry would stay the same. So like right here, this stereochemistry would end up being the same. But whenever you have like something that used to have stereochemistry as part of the double bond, you just draw it as a line because that represents it's being trigonoplanar. Okay? All right, so 4, again, it's going to be E2, and there would be no Sn2 reaction. So we would end up with the same sort of products, except now the Hoffman product will be our major product because we're using a strong, bulky base. 5, this is one of those anti-periplanar questions. So again, we will have to make our double bond between the leaving group and the carbon that has the hydrogen that is trans to the chlorine. That would be this bond right here. And then this dotted line right here would stay the same. Okay? 6 is similar, except now the carbon, this carbon right here with the dashed line of the methyl group cannot make a double bond, so we make the double bond right there. All right, so 7, this is one of the ones where you had to pick all of the possible products. So the first one, that would have been E2 plus Sn2. So we'll pick all of those products. I noticed that, I know I said to focus on E2 or like elimination as a whole, but it's important to recognize that we would get 1, 3, and I wrote 3 twice. That should be 4. Apologize. But 7 would have these 3 products, okay? And then for 8, if we replaced OH with that weak base, weak nucleophile, we would end up with all 4 products. So 1, 2, 3, 4. Okay? So that's the summary for those questions. I hope they were hard enough. Somebody said, is the major 3 sorry, which one are you talking about? Number 3, the major is the major product because the weak, they're the strong small base can make the Zeit-step product, and that major product is the Zeit-step product. Does that make sense? Anti-periplanar doesn't really matter much for things other than cyclohexanes, and this is again, or cyclos, I guess, in general. This is because you're right, because when we have single bonds that are not part of a cyclic compound, those can rotate freely, so we can rotate the hydrogen wherever we want. Okay? Does that make sense?
So like, because in the book they had said something about elimination. You want the beta hydrogen to be coplanar with the leaving group.
Yeah. Well, the thing is you can rotate.
Because like originally in the on number 3, I think you had the hydrogen as a dash, which is and the chlorine was also a dash. So I thought you had to rotate it so that the.
Oh yeah, you would have to rotate it, but the thing is you don't really have to take that into account unless you're doing cyclo, because we can freely rotate around single bonds.
Oh, okay.
Does that make sense?
Okay, so I don't have to worry too much about rotating when it's like not cyclic.
Yeah, don't worry too much about that.
Okay.
And then for carbocation shift, somebody asked, can you shift more than once? You can only really shift more than once if you're going like constantly up to a more stable version. Like for example, this is a primary carbocation that can shift into a secondary carbocation, which then can shift into that tertiary carbocation right next to it. But you wouldn't shift like from a secondary to a secondary, okay? So for 8, you could have shifted twice. Yes. Wait. Oh, I'm sorry. Did I draw that wrong? Wait. No, you wouldn't have shifted twice because you're on a secondary carbon. That secondary carbon won't shift to another secondary carbon. It only will shift to an additional tertiary carbon. Okay? Does that make sense? Okay, awesome. All right, so the last thing I'm going to go over before we're done, because we've been going for a while, is finally going to be E and Z conformations. And I'm not going to go over naming because I'm a little tired and my voice is going out, but I will talk about EZ conformation because that is a problem area that some of you have been having. So before, we've been talking about things as cis or trans. We can use cis and trans only when we're comparing sort of groups that are exactly the same. So like, for example, if we have 2 hydrogen groups on either side, and then chlorine and then bromine or whatever. Hydrogen, hydrogen, chlorine, bromine. So we can consider these cis, this is cis, and this as trans, because the hydrogens are the same group and they're on the same side in the cis and they're on opposite sides in the trans, okay? However, if you have all different groups, So like, for example, if instead of having a hydrogen there, you had a fluorine or something, bromine, chlorine, and H, now you cannot do cis and trans, and instead you have to do E or Z. The way to do this is what you do is you sort of cut this double bond in half, and you take each half one at a time. So the first thing, what you're going to do is you're going to compare the priorities of each group on one side of the double bond. So bromine will be a higher priority than fluorine because it has a higher atomic number, a higher mass. Okay? So we're going to say bromine is the high priority on this side, fluorine is the low priority on this side. Okay? Over on the other side, we say, okay, obviously chlorine will be the high priority because hydrogen is always the low priority. So low here, high here. So the way that you tell if this is E or Z is if you tell the relationship between the highs and the lows. So what I always do is I looked at the highs. So you can see here the highs are on opposite sides. So we're going to call this E opposite. So it's going to be E. The same thing we can do if they are the other way. So like this and this. So chlorine again is high, hydrogen is low, bromine is high, fluorine is low. The highs are on the same side, so we're going to say it's on the same side. I think my pen is running out of battery. So we're going to say this is Z. Okay? So the reason why we have to use E or Z is because we cannot rotate freely about the double bond like we can single bonds. Somebody said if there's less than 2 hydrogens, you'd use E and Z instead of cis and trans. Yes, basically. And you can't really make cis and trans equivalent to E and Z because of how the naming works and all that stuff. So don't rely on E always being trans and Z always being cis because that's not always how it works. So always look for E and Z. So what do you do if there's isn't a substituent on the side? I don't think I understand because, for example, if instead of having two different substituents there, we had 2 hydrogens, we cannot do E or Z conformation because these 2 are the same. They'll be exactly the same. We won't have a high or low priority. In addition, we cannot do cis or trans because this hydrogen is trans to this hydrogen, but cis to this one. So how would you know which one? So in this one, you could not do cis or trans or E or Z. Okay? What if it's just 3 lines? Oh, like this? You cannot do cis or trans with this because this is a triple bond. Triple bonds only have 1 bond on each side. So like, for example, this would be a hydrogen on this side and like a carbon on this side. You can't really do E and Z for these. Like the first one, but the bromine wasn't there. So like this. So whenever there isn't a space on the double bond, we always assume that any blank space is filled in by a hydrogen. So like this would be implying that there's a hydrogen right here. Does that make sense? So like if I had this here, I would know, okay, so there's 2 hydrogens sticking out of it like this. Okay? All right. So I think I'm going to wrap up for today. I'm going to get some coffee and then I'm going to study for my own tests. Are there any other questions before I wrap up? If not, I will see you next time. And a reminder, the Sn1, Sn2, E1, E2, comparison of E1, E2, etc., that will be contained in the description of the YouTube video. And I'll also send it to the chat here. All right, so I will see you next time. Good luck on your test.